welcome all of you. In previous presentation हमने देखा what is mean by phase and what is mean by component. Okay. Now today we shall discuss about what is mean by degree of freedom. Degree of freedom. The phase rule is concerned with the intensive properties of the system in a state of equilibrium. These variables are independent upon quantity of the substance that make up of system and its size. The pressure, temperature, concentration, density, molar entropy are all intensive variables. The minimum number of intensive variable which must be fixed in order to define the remaining intensive variable of the system is called degree of freedom of the system. The assignment of numerical value of freedom will enable us to describe the system completely at equilibrium. The system with degree of freedom 0, 1, 2, 3 are called non-variant, monovariant, bivariant, trivariant system respectively. If degree of freedom is 1, is called monovariant. If degree of freedom is 2, it is called bivariant. If it is 3, it is called trivariant. And if degree of freedom is 0, it is called as non-variant of the system respectively. For a given mass of gas, consider for a given mass of gas, its volume, pressure, temperature are related by equation PV is equal to nRT. For such system, the value of P and T can be varied independently, and the value of volume depends on the value of pressure and temperature. The system therefore is bivariant. That means volume depends upon the two variable pressure and temperature. Hence it is called as the bivariant. Consider now the system consisting of a liquid in equilibrium with its vapor. The temperature of this system can be varied independently. The value of temperature will fix the value of vapor pressure of liquid. The system therefore has degree of freedom 1. That means it is monovariant. Consider now the system consisting of a liquid in equilibrium with its vapor. The temperature of this system can be varied independently, and the value of temperature will fix the value of vapor pressure of liquid. The system therefore has degree of freedom of 1. That means it is monovariant. Finally, consider the system in which three phases of water, namely water, ice, and water vapor, coexist in a state of equilibrium. This occurs only at a particular pressure and temperature. Thus, when we say that the three phases of water coexist at equilibrium, the system becomes non-variant and degree of freedom of such system is 0. In a chemically reactive system, the number of components is given as C is equal to N minus E, whereas where N is the number of chemical species and E is the relation, that means is the number of independent equation relating the concentration of N species. These are some examples. That means explain why KCl, NaCl water system should be regarded as three component system, whereas KCl, NaBr water system should be regarded as four component system. We know that number of component and E is the number of independent equation relating their concentration. For the KCl, NaCl water, N is equal to 3. इक्विलिब्रियम क्या है, रिलेशन उसका क्या है, 3 है. Since there is no equation relating this concentration, therefore E is equal to 0. Number of component कितने हैं, KCl, NaCl, water, इसीलिए number of component कितने हुए, 3. रिलेशन कोई भी नहीं है इसीलिए 0. इसीलिए जब करेंगे C is equal to N minus E, तो C is equal to 3 minus 0 is equal to 3. For KCl, NaBr water, here KCl, NaBr, NaCl, KBr water, there one component number N is equal to कितना है, 5. और रिलेशन क्या है, 1 है, 1 रिलेशन है. इसीलिए C is equal to N minus E, तो 5 minus 1 is equal to 4. These are some again examples. With the help of this example, you can learn easily. These are the examples. This is also the examples of calculating degree of freedom. This is also the example of degree of freedom. See here, calcium chloride, water molecule, Ca plus 2, Cl minus 2, H2O gas, H2O liquid. 1, 2, 3, 4, 5. True equilibrium. Suppose that the system contains only ice at minus 5 degrees. At constant pressure, if heat is supplied to ice, its temperature will be increased and 0 degree C ice will begins to melt and the equilibrium between ice and water is established. Hereafter, the supplied heat will be utilized in melting of the ice. The temperature of the system will not change as long as the two phases coexist in a state of equilibrium. Once all the ice is melted and system contain only liquid water, the temperature of water begins to increase on applying heat and the same equilibrium in state, namely ice in equilibrium with water, can be achieved starting from the system containing liquid water only and lowering its temperature. Thus the above equilibrium can be attained from both the sides. That means from ice and also from liquid water. Such an equilibrium is called as true equilibrium. Suppose now the system contains liquid water. By cooling the water carefully at a constant pressure, it can be made to exist in the liquid state below a temperature 0 degree C. At each temperature, liquid water is in equilibrium with its vapor. The water so obtained is called as supercooled water. This state of equilibrium can only be attained from one side only, that means from water side and not from the side of ice. This is because we do not have superheated ice. This equilibrium is therefore different from the true equilibrium and is called as metastable equilibrium. On slight disturbance, say a stirring or addition of small pieces of ice will convert the supercooled water into ice. Finally, Consider a system containing almost saturated aqueous solution of sodium chloride. The rate of dissolution of sodium chloride becomes very less. However, the equilibrium will not be attained until a saturation limit is reached. Once this happens, dissolved sodium chloride will be in a state of equilibrium with undissolved solid sodium chloride. A state of solution prior to saturation is said to be unstable equilibrium. Such a state rate of approach of system to equilibrium is very slow, and the system appears to undergo no change with time. The similar situation will raised in any system that is approaching a state of equilibrium, and we can say that the system is in a state of non-equilibrium. Thank you for watching.